Hey guys, my name's Andrew Muir. I'm a freshman meteorology student here at OU, and I just wanted to share some of my thoughts on the upcoming severe weather event on Tuesday. And I'm going to preface this by saying this wasn't necessarily this didn't. I'm coming back and doing this like initial slide after I did the rest of this, and it's like half my thoughts and half like physical processes that sort of play into how storms develop. So that's what that's all about. But anyway, there's this big um, area that the Storm Prediction Center has outlined for some severe weather on Tuesday. This 30% area down from South Central Oklahoma up through the Kansas City metro area up to the Missouri Southwest Iowa border, and then 15% surrounding that and sort of extending to the east there. And then we have our 500 millibar plot here, the big sort of trough that I'm pretty sure was responsible for a lot of the severe weather over the southeast over the last few days is gradually shifting off to the east towards the Atlantic. And then you can actually see the start of this sort of initial system that's going to come through and drape a cold front across the central United States on Monday. You can see that coming in here towards the Pacific Northwest area. And then if we look at our 850 millibar chart, we can see that southerly low-level flow from the Gulf of Mexico has begun over southern Texas and adjacent northern Mexico there. So the moisture return is beginning. And then if we look at some trends, this is just the GEFS mean output, and this isn't necessarily a trend, right? This is just three little images here, but it's indicative of a larger trend. I just picked three specific runs here, and at first we were kind of seeing this more. Now I'm not saying positively tilted in a bad way, but this sort of weaker looking trough, but sort of more removed to the west. Um, that was what had been shown for several days, and that wasn't necessarily because each individual run of the ensemble or each individual member of the ensemble showed a trough that looked like that. It's really just sort of the average of all the noise that there was. And as we've come closer to the event, now we are still 4 days out, but as we've come closer, um, the each member has sort of there's less spread. If you were to look at a spaghetti plot, which COD has, and I think is great, if you were to look at that, all the lines of these 500 millibar heights have come into a lot more agreement across all of the members of the ensemble, and it's showing just kind of this almost this classic looking setup here with this sort of broad enhanced region of this broad region of enhanced mid-level flow, and this sort of this bigger trough here with sort of a shortwave maybe moving through it. A little hard to tell, obviously, from a just an ensemble sort of mean output here, but a pretty decent chance here at some modest potential instability values being reached. But notice here, this has really come to light in the most recent runs. This little sort of blip here, that's a like smaller shortwave contained within this belt of uh, a smaller subtropical jet, which if you've been watching the last few runs or several runs actually, the GFS, there's been it's had a lot of sort of mid-afternoon convection go up across Texas as a result of this, which could definitely have implications up here in Oklahoma. Say if we have Anvil blow off and that is affecting our heating, if a storm were to go up near the DFW Metroplex or something. So that is definitely something to watch, the influence of this subtropical jet and associated sort of weaker and diffuse shortwave is also going to need to be watched, and potential height rises on the backside of it, which are not favorable to convection initiation. But we will see. The members have different interpretations of this. Okay, and then moving on here, looking at the Sunday to Monday time frame, this is GFS output. We see from the shortwave, which is actually visible here, this sort of lead shortwave over the Pacific Northwest here, ends up dragging a cold front through the central United States from the Texas Panhandle up towards Lake Michigan. And that actually sort of stunts the northward return of deeper and better low-level moisture, if you will. But that's not to say that moisture return is not happening. It still is. It's just sort of being held over Texas during this time frame. And with this more southwesterly flow uh, ahead of the cold front, that's why we're seeing more of a severe risk sort of displaced to the east, as opposed to the original outlooks from eastern Oklahoma up through Missouri in this time frame. But look at how deep and how far south these low-level southerlies extend. I mean, the entire north-south length of the Gulf of Mexico is experiencing this southerly flow, which is really going to be bringing in some deep tropical moisture. And then we are also looking at, in this same time frame, a persistent and westerly mid-level flow advecting an EML from the desert southwest, where there is strong heating from the sun in the daytime, which results in these really vertically expansive mixed layers with low dew points but strong lapse rates, and that sort of goes over top of our warm and moist low-level air that oftentimes will get advected northwards in the Gulf of Mexico in typical plain severe events such as this one. Oh, look at that. And yeah, this is just a sounding I pulled from like eastern or western New Mexico area, showing those steep lapse rates. I think that says about 8.2 Celsius per kilometer. So definitely the development and subsequent advection of the CML, as always, generally in plain severe events, is playing a significant role. And just this constant broad 700 millibar to 500 millibar flow is going to advect that to the sort of region of interest, if you will. And then moving into Tuesday morning, that moisture in Texas is finally going to be free to flow north, as the second shortwave that's coming behind that initial shortwave that draped that cold front down the plains is going to result in a pretty rapid intensification of a surface low from central Colorado, sort of ejecting into northwest Kansas and adjacent Nebraska there. So that's going to result in a really strong response from the low-level winds. And as you can see, as predicted by the Euro, sort of the remains of that cold front kind of get washed out as that low-level flow accelerates and our moisture is advected northwards. This is only within the span of 6 hours in the morning too. So pretty impressive there. And the moisture down in Texas is already likely going to be of good quality. It's just a matter of how far north it'll be advected. And I'm mostly going to focus on the severe potential for Oklahoma, maybe up into parts of south central Kansas, but there most certainly exists a risk all the way up into the Kansas City metro, into Iowa, that area. But I'm mostly going to focus on the Oklahoma area. But yeah, essentially that moisture it's just south of Oklahoma. It just needs to work its way into Oklahoma, which really shouldn't be a problem based on how things are looking right now. As we move into Tuesday afternoon, that's when we're really, we're getting closer to, what everybody's waiting for. And the GFS seems to erode convective inhibition by about 21Z, but that does not always coincide with convection initiation. There's other processes that have to go on there for that to occur. And what we're likely going to see is with the erosion of the convective inhibition, the development of a cumulus field along the dry line, which is actually going to help us out a lot. Obviously, you need clouds or storms to form, right? But there's other processes that go on here too. As these initial cumulus clouds go up, right? We got our sort of wide, healthy cumulus here. They entrain the dry air that is residing at the base of the EML, directly above the what looks to be a very well-mixed boundary layer per most model output. They're going to entrain that dry air, and that's why those initial cumulus aren't going to reach. Maybe even if they have reached their LFC, they're definitely not going to reach their EL because they're going to be fighting all this dry air. But as those cumulus clouds go up and dissipate the moist air that effectively originated from below the EML, It's going to get detrained back out into the atmosphere, um, and gradually moisten the lower EML, which will be, now if we had a lot of, say, we were launching weather balloons, say every 30 minutes or so, you'd see the dew point trace moving farther to the right, coinciding with increasing relative humidity in that level of the atmosphere, which then reduces the amount of entrainment other infant cumulus have to deal with. And basically, you sort of nudge your way up towards convection initiation. So that's what we're going to watch for. And convection initiation here is not guaranteed by any means. So this is going to be really interesting to watch. But the erosion of SYN in the mid-afternoon, along with the southerlies going along the dry line, means that there's going to be, one, with the erosion of SYN, likely a pronounced cumulus field by, say, 5 or 6 p.m., and two, with the low-level flow sort of in line with the dry line circulation, means these clouds that are forming are going to be within the sort of vertical circulation of the dry line, which also increases our chances of convection initiation. And this process of rising and falling cumulus with all this entrainment and detrainment, it's a gradual process. To me, I guess, I feel like convection initiation always takes longer than I think it will, 90% of the time. Sometimes it's like boom, but there are some, this process is not unique also. This isn't unique to this event. This is how a lot of times how we get convection initiation, with sort of subtle forcing or a really sort of low RH in the EML layer. But we can also look at what's influencing this process. And the southerly flow along the dry line, and also southerly flow not only at the surface, but in the 0 to 1 kilometer layer, parallel with the dry line, is going to keep these infant cumulus clouds, some of them not infant cumulus clouds, but your cumulus field, a lot of your rising air is going to be kept within the sort of vertical circulation of the dry line, for miles and miles as it gets advected northward. So that's favorable towards convection initiation here. And then two key trends that I've sort of honed in on, things I'm going to watch, is one, obviously moisture quality. Moisture quality is always a question. And the Euro has maybe some less optimistic, if that's the term you want to use, on moisture return. But it also seems to have this weird, like, non-dry line feature. So there might actually be some physical sort of wrongness to the Euro, but that is pure speculation, and I don't know. So, but then also, how does the orientation of the dry line and the Cape field evolve? One thing that I notice with a lot of model runs is sort of these very subtle, but these changes that accumulate over time, even if it's just the orientation of the Cape field, like where is our strongest potential instability relative to a boundary, or just how does this look? This is stuff that kind of tends to shift very slowly on model runs sometimes. But all of a sudden it's like 5 runs later, you're looking at a completely different looking event than you were. So something to keep in mind. And say if our dry line changes in orientation, that's going to affect how long air's in that sort of rising side of the dry line circulation. So that's just definitely something to watch. So sort of getting into more of the nitty gritty here of some of these processes I was talking about. Looking thermodynamically, we have what likely will be a well-mixed boundary layer at the time of potential convection initiation, which promotes turbulence within the boundary layer. You get a cumulus field developing, all that. You reduce your SYN to allow for greater cumulus development. And then if we sort of take the mean wind of the, say, 0 to 2 kilometer layer, the depth, if you will, of the infant updrafts, we can sort of estimate their initial motion roughly. And this is just something I've been trying out lately. And if you want more on this, sort of updrafts rooting within their layer, how that relates to CI, check out John Peters' new paper. But these initial updrafts aren't going to be that tall, right? Because they're going to have to be dealing with that entrainment. And like I said before, you get one cloud, or one sort of updraft that passes its LFC. It's not going straight to the EL. It's just not happening. So these initial updrafts are going to be rather shallow, and they're not going to move with the 0 to 6 kilometer mean wind. They're just not, because they're not going to be extending up to maybe even half that height. So the winds above the top of the updraft don't really matter that much at first, because the updraft just simply isn't feeling it. So the updrafts are kind of going to move with the mean wind of, say, the 0 to 1, 0 to 2 kilometer layer, which happens to be, as of now, relatively parallel to the dry line. And it's parallel, but with a little bit more of a sort of off dry line easterly component, which, instead of taking them over into the dry side, is going to sort of nudge them, if you will, to the eastern moisture side, especially as these updrafts gradually root within a deeper layer, feel stronger storm relative flow, and become wider and ready to do their thing, essentially. And then you're going to get that gradual sort of veering of the updraft motion vector. So this hodograph, in combination with the dryline orientation, looks rather favorable for convection initiation, even in the presence of, say, neutral sort of height tendencies, which is obviously a thing that will have to be worked out. And this is essentially speculation at this point, because we're still 4 days out. So, right, in order for there to be storms, or for us to care about what the storms are going to do, we actually need storms to happen, right? But these aspects here look favorable towards CI. Now, obviously, if storms go up too early, say in Texas, and then, oh no, we've got some crazy stuff going on from these things, and that messes up our convection initiation chances, or CI is not guaranteed. CI is not guaranteed. Let's just make that clear. So I'm going to move on to this here. When we're talking about storm relative flow, we need storm relative flow for wider updrafts that are going to be able to withstand the negative effects of the entrainment that's going to happen here from the dry air within the EML. Once they get past their sort of like safe boundary layer, they're going to entrain that drier mid-level air. Now, we need wide updrafts to be able to withstand that, the negative effects of entrainment. And there's two ways that you can increase storm relative winds. And increasing storm relative winds is strongly correlated with storm relative inflow, which leads to wider updrafts. And there's essentially two ways in a hodograph sense that you can do that. One is something I call storm motion dragging, which essentially is strong shear, sort of above like 1 kilometer or so, dragging that storm motion vector away from the low level winds, right? And that's going to increase sort of the length of your vectors, if you will, between the storm motion and the low level wind, which obviously stronger storm relative flow, which leads to wider updrafts, better chances at convection initiation, and also just higher W values in the upper level of the storm. But the increasing shear in the mid levels is not the only way to do this. The other way to do it is sort of through this hodograph curvature technique. Not really a technique, it's just something that happens. But so this was from that day in Illinois, where there was a bunch of tornadoes really just come out of these really small bases of thunderstorms initially. And if we look here, the storm relative wind values from the surface to 1 and surface to 3 kilometer layer, between this Illinois case and then the Panhandle case back in March of last year, almost identical. even with these completely different hodographs and shear distributions. Well, how is that possible? Well, in this case, on the left, the shear is dragging the storm motion away from the low-level hodograph, but in this case on the right, the curvature is resulting in a storm motion that is far away from the low-level portion of the hodograph. If this was a straight hodograph, you would have much less storm relative flow. So this curvature is really key here to increasing your storm relative winds. And now these are not necessarily high storm relative wind values by any means, but they were high enough for supercell development on the 9th of August. So there's two ways in which you can achieve this sort of storm motion removal from the low level winds. And this upcoming Tuesday is definitely going to be a case of hodograph curvature. So before we keep going, I just want to do a little word on CAPE, if you will, because the GFS and the NAM and the models are showing a good bit of potential instability, high CAPE values. And I should just start by saying on its own, CAPE is not an accurate indicator of updraft strength. It's just not, because there's so many other things that are going on in the proverbial, parcel, right? It's mixing with air from above the level it originated. It's drawing in this dry air from, say the EML region. It's condensating. There's hail forming in it. There's rain forming within this parcel. And all these things are really ultimately working to dampen the vertical acceleration of an updraft. So how do we measure, how do we measure potential updraft strength then? Well, a wider updraft is going to sort of minimize the interaction and at the very least minimize the negative effect between or the negative effect of drawing in this less buoyant environmental air into the updraft, because this updraft core in a big updraft, right, it's going to be protected from that air being drawn into it. And how do we get wide updrafts, right? Larger storm relative inflow. So right inflow to a storm, and that's very strongly correlated with increasing storm relative winds. That leads to wider updrafts, and they're more resilient to the negative effects of entraining less buoyant air, and are able to realize a higher percentage of their CAPE. That's why I've been calling CAPE potential buoyancy, because it is, quite frankly, it's only potential. An updraft has to be in a certain state to use a significant proportion of that CAPE. So a wider updraft it's going to be able, if we were able to track the temperature inside the center of a wide updraft, it would more closely follow the dotted parcel path you see plotted on a sounding than the fringe of the updraft or the core of a smaller updraft, because all this air rising is more sort of suited to take on this entrainment and hydrometeor loading. So yeah, so just because there's large CAPE does not mean that there's going to be large vertical accelerations within the updraft. Storm relative flow is going to modulate that, and then the sort of tilting of vorticity, and then your rotationally induced pressure deficit within the updraft is actually going to regulate a lot more of the updraft acceleration in the lower half of the storm. So CAPE on its own is just not a good indicator of updraft strength. But in this event, we are going to have sufficient storm relative flow if storms go up at, say, 5 or 6 p.m. to utilize a large chunk of this big CAPE profile. Okay, so finally, if a storm goes up, we've got a good cumulus field. It's the low level flow is rather parallel to the dry line. and by God, a storm goes up. What's going to happen? So taking a look at this little GIF here, we see as the day progresses, and initially you really don't have a favorable shear or storm relative sort of wind profile at all. It really only starts to get favorable about 22, 23Z, 5 or 6 p.m. as the low-level jet starts to really ramp up, and that is gonna, you see the 0 to 3 kilometer part of this hodograph just blow up, right? This strong system is going to induce a really strong LLJ. So that's what we're looking at there, and that results in, you see the shear here going up, 0 to 1 kilometer shear and potential vorticity, right? Because shear is the sort of, shear is what, vorticity is the cause of shear. So the more shear you have, essentially more spin the storm's able to take in. And we have 30 plus knots of 0 to 1 kilometer shear by 0Z, which is, that's no joke. And you can see the cap here getting eroded throughout the day, along with the sort of gradual moistening of the boundary layer. This is up in Lamont, north central Oklahoma. And the storm relative flow increases to this supercell threshold, which a couple studies have sort of indicated as 0 to 2, 0 to 3 kilometer storm relative flow of around 20 knots is necessary for supercell development. It increases to that sort of threshold by 22Z. So it looks like the cap should hold things off until then. Now, obviously, like I was saying, the influence of that subtropical jet, or the subtropical jet with the sort of associated broad and diffuse little shortwave there, that could play some games here. So that definitely has to be watched. But if we're thinking about a classic, plains dry line setup, and oh my gosh, it held off till 5 or 6 p.m., which is possible. There is definitely the potential for some pretty significant stuff come out of these storms. And it's pretty evident here. I mean, just look at how large the low-level hodograph gets. Just the amount of potential vorticity there it's just massive. And notice that there's not really that much shear above 3 kilometers. And this kind of goes back to what I was saying earlier, where your storm motion is removed from the low-level part of the hodograph thanks to the extreme curvature and low-level shear, not mid and upper-level shear, dragging the storm motion away. So that's just something to note. So, and the physical effect of, say, mid-level shear is I don't think we really have a good grasp on it. That's something actually I'm looking into right now. So this will be interesting to see what plays out here, but definitely a look of a very potentially sort of significant, there's a pretty high ceiling here if the storm were to go up, for sure. I mean, we have a large Cape profile, which, given our storm relative flow, right, our relatively large storm relative flow, a good chunk of that should be able to be taken advantage of, and sort of aid in that, updrafts being able to reach their at least somewhat close to the thermodynamically predicted maximum W. And then the ingestion of vorticity in low 3 kilometers. I mean, when you have that much shear, in a sustained storm moving into an environment like that, it doesn't really take too much to get a strong mesocyclone there, strong low-level mesocyclone. So yeah, thanks for watching, guys. I really appreciate it. And we'll see what happens. So yeah, thanks.